What if I told you that the universe might not be what it seems? That hidden within the fabric of reality are secrets so profound, they could rewrite everything we thought we knew about space and time. Quantum space-time, a concept that sounds like it belongs in science fiction, might just hold the key to understanding the very essence of existence. Think about this: the tiniest quantum fluctuations, those ripples in the fabric of reality, could be creating microscopic wormholes connecting distant parts of the universe in ways we're only beginning to grasp. These aren't just abstract ideas, they're discoveries that are reshaping our understanding of the cosmos, bridging the gap between quantum mechanics and Einstein's theory of general relativity. But here's the real kicker. What if the universe itself is a giant quantum computer processing information at a scale so vast it's beyond human comprehension? Today, we're diving into 35 extraordinary discoveries in the realm of quantum space-time revelations that will challenge your perception of reality, from the tiniest particles to the vast expanse of the cosmos. Get ready to explore mind-bending concepts, groundbreaking theories, and the latest research that's pushing the boundaries of science. This isn't just a journey through space and time, it's a journey into the very heart of what makes the universe tick. Let's begin. Picture this: two particles separated by light years of empty space, yet somehow communicating instantaneously, as if the vast distance between them doesn't exist. This isn't science fiction, it's quantum entanglement, a phenomenon that defies everything we thought we knew about how the universe works. When one particle changes its state, the other responds instantly, no matter how far apart they are. It's as if they're connected by an invisible thread weaving through the fabric of reality itself. This bizarre behavior hints at something profound, a deep connection between quantum mechanics and the very structure of space-time. Physicists call this non-locality, a concept that challenges the classical idea that objects can only influence each other through direct local interactions. Albert Einstein famously referred to entanglement as spooky action at a distance because it seemed to violate the speed limit of the universe, the speed of light. But rather than dismissing it as a quirk, modern researchers see entanglement as a key to unlocking the mysteries of quantum space-time. Experiments like the Bell test have confirmed that this phenomenon is real, not just a theoretical curiosity. In these tests, scientists measure the properties of entangled particles to see if their outcomes match predictions. Time and again, the results show that entanglement is a fundamental feature of the universe, not an illusion or a trick. To make sense of it, think of the universe as a cosmic web where every particle is subtly linked to others, no matter how far apart they seem. Entanglement might be the threads that hold this web together, hinting at a deeper layer of reality where distance and time don't behave the way we're used to. And while entanglement is astonishing on its own, it's likely just the beginning. What other secrets might quantum space-time hold? The answer could reshape our understanding of everything from black holes to the origins of the cosmos. Imagine if the universe had secret passageways, hidden shortcuts that could bend the rules of space and time. This isn't science fiction. It's the fascinating idea behind wormholes, cosmic tunnels that could connect distant parts of the universe in an instant. And believe it or not, this concept is inspired by something much smaller: the strange behavior of quantum particles. In the quantum world, particles like electrons can perform what's called quantum tunneling. This is when a particle seemingly cheats its way through an energy barrier it shouldn't be able to cross, almost like slipping through an invisible wall. Now, physicists have wondered, if particles can tunnel through barriers, could space-time itself have similar shortcuts? That's where wormholes come in. Wormholes, also known as Einstein-Rosen bridges, are theoretical structures that link two separate points in space-time. Picture folding a piece of paper so that two distant dots touch. Wormholes could be the cosmic equivalent of that fold. These structures aren't just random ideas, they're rooted in Einstein's theory of general relativity, which describes how massive objects warp space and time. Renowned physicist Kip Thorne took this idea even further, exploring how wormholes might be stable enough to traverse, assuming we could find or create one. While they remain purely theoretical for now, wormholes offer a tantalizing glimpse into how space-time might be far more interconnected than we ever imagined. So, if wormholes are the cosmic shortcuts, what could create them? That's where quantum fluctuations come into play. These tiny, random changes in energy at the quantum level might hold the key to forming these elusive tunnels. But how? Well, that's a story for our next discovery. In the seemingly empty void of space, there's a hidden world of constant activity, a place where particles flicker in and out of existence, defying our everyday understanding of reality. This is the quantum vacuum, a state of energy so rich and dynamic that it's anything but empty. Here, quantum fluctuations reign supreme, creating a cosmic dance where particles briefly emerge and vanish in a heartbeat. But these fluctuations aren't just random noise, they're the architects of space-time itself, shaping the very fabric of the universe in ways we're only beginning to understand. At the heart of this phenomenon are virtual particles, pairs of particles and antiparticles that appear spontaneously, only to annihilate each other moments later. Though they exist for the briefest of moments, their impact is profound. Take, for example, the Casimir effect, where two uncharged metal plates placed close together experience an attractive force. This happens because the space between the plates restricts the types of quantum fluctuations that can occur, creating a pressure difference that pushes the plates together. It's a tangible demonstration of how virtual particles, though fleeting, can influence the physical world. Quantum field theory takes this even further, suggesting that these fluctuations might do more than just create tiny forces. Some theories propose that they could form microscopic wormholes, shortcuts through space-time that connect distant points in the universe. Others speculate that these fluctuations could play a role in the universe's expansion, potentially offering clues about the mysterious force we call dark energy. Picture space-time as a bubbling quantum soup, where every bubble represents a fluctuation, and every stir of the spoon alters the structure of reality itself. What's truly fascinating is how these quantum fluctuations might hold the key to some of the universe's biggest mysteries. Could they be the source of dark energy driving the accelerated expansion of the cosmos? Or might they reveal deeper connections between quantum mechanics and gravity, two realms of physics that have long resisted unification? As we explore these questions, we're reminded that even the emptiest corners of space are teeming with possibility, waiting to reveal their secrets. And in this quantum dance of creation and destruction, the universe whispers its deepest truths. Imagine the universe as a vast, ever-expanding balloon. Now, picture an invisible force pushing on that balloon, making it grow faster and faster. This mysterious force is what scientists call dark energy, and it's one of the greatest puzzles in modern physics. We know dark energy exists because it's causing the universe to expand at an accelerating rate. But what exactly is it? Here's where things get fascinating. Quantum space-time might hold a key to understanding this cosmic enigma. At the tiniest scales, the fabric of space-time isn't smooth and calm. Instead, it's a seething sea of quantum fluctuations, where particles pop in and out of existence in a chaotic dance. These fluctuations aren't just random noise, they could be generating a kind of energy that permeates the universe. This energy, known as vacuum energy, might be the source of dark energy itself. Think of it like the hum of a cosmic engine, constantly running in the background, pushing space apart. Cosmologists have long wondered how to connect the bizarre world of quantum mechanics with the grand scale of general relativity, Einstein's theory of gravity. Dark energy could be the bridge between these two realms. Some theories suggest that the quantum vacuum, the energy of empty space, might be leaking into the cosmos, driving the accelerated expansion we observe. It's as if the universe is being stretched by an invisible cosmic wind, one born from the quantum realm. But how do we test such an idea? Scientists are looking to the universe itself for clues, studying the distribution of galaxies and the cosmic microwave background to trace the fingerprints of dark energy. And while we're still piecing together the puzzle, one thing is clear. Dark energy isn't just a curiosity, it's a fundamental part of the story of our universe. It's a reminder that even the emptiest corners of space are buzzing with activity, shaped by the strange rules of quantum physics. Now, as we peer deeper into the cosmos, another mystery beckons, one that might reveal even more about the quantum nature of space-time. Black holes, those cosmic behemoths, could hold the answers, but that's a story for the next discovery. Black holes are among the most mysterious objects in the universe, regions where space and time are so warped that nothing, not even light, can escape their gravitational pull. At their core lies a singularity, a point where the curvature of space-time becomes infinite, and our current understanding of physics breaks down. This extreme environment creates a fascinating clash between two of science's most successful theories, quantum mechanics and general relativity. While general relativity describes black holes as smooth, predictable entities, quantum mechanics suggests that information, like the properties of particles, can never truly be destroyed. This tension gives rise to one of the biggest puzzles in modern physics, the black hole information paradox. Imagine a black hole as a cosmic shredder, swallowing stars, planets, and anything else that crosses its event horizon. According to classical physics, all that information about what fell in would be lost forever, erased from the universe. But quantum mechanics insists that information must be preserved, even if it's scrambled or transformed. This paradox has left scientists scratching their heads for decades. Enter Stephen Hawking, who proposed a groundbreaking idea: black holes aren't entirely black. Through a process now known as Hawking radiation, black holes slowly emit particles and energy, causing them to shrink over time. But here's the catch: Hawking's theory suggests that this radiation carries no information about what fell into the black hole, seemingly confirming the paradox. This dilemma has sparked a revolution in theoretical physics, with researchers exploring how quantum gravity, a theory that unites quantum mechanics and general relativity, might hold the key to resolving the paradox. Could the information be encoded in the Hawking radiation after all, or is it stored on the black hole's surface like a hologram? These questions aren't just academic. They touch on the very nature of reality and how information shapes the fabric of the universe. As we delve deeper into the quantum realm, black holes continue to challenge our understanding, offering tantalizing clues about the hidden structure of space-time itself. The sixth discovery takes us into the heart of one of the most profound challenges in modern physics, the quest for a theory of quantum gravity. For decades, scientists have been trying to bridge the gap between quantum mechanics, which governs the tiny world of particles, and general relativity, Einstein's framework for understanding the vast cosmos. These two pillars of physics work brilliantly in their own domains, but when it comes to the extremes like the center of a black hole or the moment of the Big Bang, they clash spectacularly. This is where quantum gravity steps in, offering a potential unified framework that could reveal the true nature of space-time at the smallest scales. Leading the charge are two major contenders, string theory and loop quantum gravity. String theory envisions the universe as a symphony of tiny, vibrating strings, with space-time emerging from their interactions. It's a grand, multidimensional vision that suggests our reality might be just one layer of a deeper cosmic structure. On the other hand, loop quantum gravity takes a different approach, proposing that space-time itself is quantized, broken into discrete, indivisible units. Picture space-time as a woven tapestry where each thread represents a quantum loop. These loops intertwine to create the fabric of the universe, a concept championed by physicists like Carlo Rovelli. It's a radical reimagining of reality, suggesting that space-time isn't smooth and continuous but rather a dynamic, granular network. What's truly fascinating is how these theories challenge our everyday understanding of the universe. They hint at a reality where space and time are not fixed backdrops but active participants, shaped and reshaped by quantum processes. This isn't just theoretical speculation, it's a window into the fundamental nature of existence. And as we edge closer to understanding quantum gravity, we're also uncovering clues about the next mystery, the quantum nature of time itself. Could time, like space, be woven from tiny, indivisible threads? That's a question we'll explore as we dive into the seventh discovery. What if time isn't the steady, flowing river we've always imagined? What if, instead, it's more like a series of tiny, discrete steps like frames in a movie reel? This is the fascinating idea behind the quantum nature of time, a discovery that shakes the very foundations of how we perceive reality. In the quantum world, time might not be continuous at all. It could be quantized, broken into the smallest possible units, just like energy in quantum mechanics. This challenges everything we thought we knew about time as a smooth, unbroken stream. At the heart of this idea is something called Planck time, the smallest measurable unit of time, so brief it's almost impossible to comprehend. To put it in perspective, a single second contains more Planck times than there are seconds since the Big Bang. This incredibly tiny unit suggests that time, at its most fundamental level, might operate in discrete packets rather than a continuous flow. But what does that mean for our understanding of the universe? Some physicists propose that time itself emerges from the interactions of quantum particles, almost like a kind of cosmic illusion. Imagine time as a series of snapshots, each one representing a moment in the quantum fabric of space-time. These snapshots don't flow smoothly, they flicker into existence one after another, creating the illusion of movement and change. It's as if the universe is updating itself frame by frame, and we're simply experiencing the result of this quantum choreography. This radical perspective doesn't just redefine time, it also opens the door to explaining one of the greatest mysteries in physics, the arrow of time. Why does time move forward and not backward? If time is quantized, its flow might be tied to the fundamental rules of quantum mechanics, offering clues to why the past, present, and future behave the way they do. The quantum nature of time could be the key to unlocking some of the universe's deepest secrets. Why does time move forward, never backward? This is one of the most profound mysteries in physics, often referred to as the arrow of time. While our everyday experience tells us that time flows in one direction from past to future, scientists have long struggled to explain why this is the case. The answer might lie in the strange world of quantum entropy, a concept that measures the disorder or randomness in a system. In the quantum realm, entropy increases as systems evolve, creating a natural direction for time. But how does this work? Quantum decoherence plays a key role here. Imagine a quantum system starting in a highly ordered state, like a perfectly synchronized dance. Over time, interactions with its environment cause this order to break down, leading to chaos or disorder. This process, known as decoherence, creates the illusion of a unidirectional flow of time. Researchers suggest that the arrow of time emerges from these quantum interactions, as particles lose their coherence and the system becomes increasingly disordered. It's as if time is a river always flowing from order to chaos, carrying us along its current. This idea has captivated physicists who see the arrow of time not as a fundamental property of the universe but as a consequence of quantum mechanics. Some even propose that without quantum decoherence, time might not have a direction at all. It's a fascinating perspective that ties the flow of time directly to the behavior of particles at the smallest scales. And while this might sound abstract, it has profound implications for our understanding of reality, especially when we consider how quantum space-time could shape the multiverse. But that's a story for the next discovery. Picture this: what if our universe is just one leaf on an infinite cosmic tree, surrounded by countless other leaves, each representing a separate reality? This is the mind-bending idea behind the multiverse, a concept that suggests our universe might not be alone. Instead, it could be one of an unimaginable number of parallel universes, all existing simultaneously within the fabric of quantum space-time. At the heart of this idea is the many-worlds interpretation of quantum mechanics, a theory that proposes every time a quantum event occurs, like the flip of a particle's spin or the decay of an atom, the universe splits into multiple branches. Each branch represents a different outcome, creating a new reality where that specific possibility plays out. Think of it as walking through a forest where every step you take creates a new path, and each path leads to a completely different version of your journey. Cosmologists have taken this idea even further, suggesting that quantum space-time itself might be the key to unlocking the multiverse. The fabric of space-time, with its fluctuations and quantum foam, could be the fertile ground from which these parallel universes emerge. Some scientists argue that the multiverse isn't just a wild speculation, but a natural consequence of how quantum mechanics and gravity interact on the smallest scales. To make this more relatable, imagine the multiverse as a cosmic tree with infinite branches. Each branch represents a unique universe growing from the same trunk of quantum space-time. Some branches might look strikingly similar to ours, while others could be wildly different, perhaps with alternate laws of physics or even entirely new forms of life. This metaphor helps us grasp the sheer scale and diversity of possibilities that the multiverse concept introduces. But here's where it gets even more intriguing. Quantum space-time might also hold clues to one of the biggest mysteries in science, the fine-tuning of our universe. Why does our universe have just the right conditions to support life? Could the multiverse provide an answer? Stay with us as we explore how quantum space-time might explain why our universe seems so perfectly calibrated for existence. What if the universe we live in is the result of an unimaginably precise cosmic balancing act? This is the 10th discovery in our journey, the concept of fine-tuning and its connection to quantum probabilities. The idea is simple yet mind-blowing. Certain fundamental constants and laws of nature appear to be perfectly calibrated to allow life to exist. If the gravitational force were slightly stronger, stars would burn out too quickly. If the strength of electromagnetism were slightly weaker, atoms wouldn't hold together. It's as if the universe has been carefully adjusted to create the conditions for life. But how is this fine-tuning mere chance, or is there something deeper at play? Quantum probabilities offer a tantalizing explanation. At the quantum level, particles exist in a state of uncertainty, with probabilities determining their behavior. Some physicists suggest that this inherent randomness might allow for multiple universes, each with different constants and laws. In this multiverse scenario, we just happen to live in the one where the numbers add up perfectly for life. This idea is tied to the Holographic Principle, which states that we observe a life-friendly universe because we couldn't exist in one that wasn't. It's like winning the cosmic lottery. If the numbers hadn't aligned, we wouldn't be here to marvel at them. To make this even more relatable, think of the universe as a vast game of chance. where every possible combination of physical constants and laws is tried out across countless universes. Our universe is the winning ticket, the one where all the right conditions came together to allow galaxies, planets, and life itself to emerge. Some scientists even argue that this fine-tuning points to a deeper quantum structure, a hidden layer of reality where the rules of the game are written. It's a perspective that blurs the line between physics and philosophy, inviting us to question whether the universe is shaped by chance, necessity, or something even more profound. And speaking of profound, this fine-tuning leads us to the next discovery: how quantum space-time might have influenced the very beginnings of the universe. What role did these quantum probabilities play in the moments after the Big Bang? Could they hold the key to understanding why our universe looks the way it does? Stay tuned, because the answers might just reshape how we see reality itself. What if the Big Bang wasn't the beginning, but instead a moment of transformation? This is one of the most profound questions in modern physics, and quantum space-time might just hold the key to unraveling the mystery. When we peer back to the earliest moments of the universe, the story doesn't start with a singular explosion, but rather with a quantum fluctuation, a tiny ripple in the fabric of reality. Imagine the universe as a quantum bubble emerging from an endless sea of possibilities. This is the core idea behind quantum cosmology, a field that reimagines the birth of the cosmos through the lens of quantum mechanics. Physicists suggest that before the Big Bang, space and time as we know them didn't exist. Instead, the universe was in a state of quantum superposition, where multiple potential realities coexisted. Out of this quantum haze, a single fluctuation grew, giving rise to the universe we inhabit today. Think of it like a cosmic dice roll, a random event that set everything into motion. This perspective challenges the traditional view of the Big Bang as a definitive starting point, proposing instead that it was a quantum event, one that might not have been unique. The implications are staggering. If the universe emerged from a quantum fluctuation, could there be others? Are we just one of countless cosmic bubbles, each with its own set of physical laws? Theories like these don't just reshape our understanding of the universe's origins. They also open the door to explaining cosmic inflation, the rapid expansion that followed the Big Bang. If quantum space-time holds the answers, then the story of our universe might be far more intricate and far more beautiful than we ever imagined. Picture the universe just moments after the Big Bang, a chaotic, rapidly expanding sea of energy. This explosive growth, known as cosmic inflation, wasn't just a simple expansion. It was a quantum-driven transformation. During this unimaginably brief period, the universe ballooned in size faster than the speed of light, stretching space-time itself to unimaginable scales. But here's where it gets even more fascinating. Tiny quantum fluctuations, ripples in the fabric of space-time, were stretched along with it. These fluctuations, born from the uncertainty of quantum mechanics, became the seeds for everything we see today: galaxies, stars, and even the vast cosmic web that connects them all. Think of cosmic inflation like blowing up a balloon. As it expands, tiny wrinkles on its surface grow larger and more pronounced. In the same way, those initial quantum ripples were magnified, creating the uneven distribution of matter that eventually gave rise to the universe's large-scale structure. Without these fluctuations, the cosmos might have been a featureless void, devoid of the complexity we observe today. Cosmologists now believe that inflation wasn't just a physical process, it was deeply rooted in the quantum realm, where space-time itself behaves in unpredictable, almost magical ways. What's truly mind-bending is how quantum space-time played a central role in this process. The same quantum rules that govern particles also shaped the universe's earliest moments, driving inflation and setting the stage for everything that followed. It's as if the universe itself was woven together by the threads of quantum mechanics, with space-time acting as the loom. And while we can't see inflation directly, its fingerprints are everywhere, in the distribution of galaxies, the cosmic microwave background, and even the way light travels across the cosmos. This brings us to a tantalizing question. How did these quantum fluctuations leave their mark on the cosmic microwave background? That's where our next discovery takes us, into the faint afterglow of the Big Bang and the secrets it holds about the quantum nature of space-time. Picture this, a faint, ancient light that has traveled across the cosmos for over 13 billion years, carrying with it secrets from the very beginning of everything. This is the cosmic microwave background, or CMB, often called the afterglow of the Big Bang. It's like a time capsule, preserving a snapshot of the universe when it was just a newborn, barely 380,000 years old. But what makes the CMB so extraordinary isn't just its age. It's the tiny ripples etched into its surface, whispers of quantum fluctuations from the earliest moments of existence. These ripples, no larger than 1 part in 100,000, are like cosmic fingerprints. They're the imprints of quantum mechanics at work in the fabric of space-time itself, stretched and amplified as the universe expanded. Imagine throwing a pebble into a calm pond. The ripples that spread outward are a faint echo of the initial splash. In the same way, the CMB's ripples are echoes of the quantum chaos that once ruled the universe, frozen in time and preserved for us to decode. Scientists studying the CMB have discovered that these ripples hold clues to the nature of quantum space-time. By analyzing their patterns, researchers can test theories about how gravity and quantum mechanics might have interacted in the earliest moments of the cosmos. Some even believe that these ripples could help us unlock the mysteries of quantum gravity, a theory that would unify Einstein's general relativity with the strange rules of the quantum world. It's as if the CMB is a cosmic Rosetta Stone, offering us a language to translate the quantum origins of the universe. And here's where it gets even more fascinating. The same quantum fluctuations that created these ripples might also hold the key to understanding dark matter, the invisible substance that makes up most of the universe's mass. Could the same quantum processes that shaped the CMB also have seeded the structures we see in the cosmos today? It's a tantalizing question, one that keeps researchers poring over the CMB's subtle patterns, searching for answers that could reshape our understanding of reality itself. Imagine a universe where most of what exists is completely invisible to us. That's the reality we live in because dark matter, the mysterious substance that makes up about 85% of the universe's mass, doesn't interact with light. You can't see it, touch it, or even detect it directly, yet its gravitational effects are everywhere, shaping the cosmos in ways we're only beginning to understand. But here's where things get even more intriguing. Quantum space-time might hold the key to unraveling this cosmic enigma. Scientists believe that dark matter could be tied to exotic quantum particles or fields that exist beyond the standard model of physics. These particles might interact with the fabric of space-time in ways that are so subtle, they've eluded detection so far. Some physicists suggest that dark matter could even be a byproduct of quantum gravity, a force that operates on scales so small and so fundamental, it's almost impossible to observe directly. Think of dark matter as the cosmic glue. It doesn't just pull galaxies together. It might also be a bridge between the quantum world and the vast expanse of the universe. This idea has led to groundbreaking theories, like the possibility that dark matter particles could warp space-time itself, creating ripples that influence everything from the formation of galaxies to the behavior of light. It's a tantalizing thought. What if dark matter is not just a passive bystander in the universe, but an active participant in the quantum dance of space and time? As researchers continue to explore these connections, one thing is clear. dark matter isn't just a missing piece of the cosmic puzzle, it's a doorway to understanding the deepest secrets of quantum gravity. And speaking of cosmic puzzles, this brings us to the next discovery, where we'll explore how quantum space-time might shape the birth and evolution of galaxies themselves. What if the very fabric of reality is woven into the structure of the universe on the grandest scales? Galaxies, those colossal collections of stars, dust, and dark matter, didn't just appear out of nowhere. Their formation is a cosmic ballet choreographed by gravity and guided by something far more subtle: quantum fluctuations. Picture the early universe, a hot, dense soup of energy and particles. Tiny ripples born from the quantum realm began to ripple through this primordial chaos. These weren't just random blips, they were the seeds of structure, the first whispers of what would become galaxies. As the universe expanded and cooled, gravity took hold, pulling matter together around these quantum seeds. Over billions of years, these clumps grew denser, collapsing under their own weight to form the first galaxies. But here's where it gets fascinating. The distribution of galaxies we see today isn't random. It's a direct reflection of those early quantum fluctuations. Cosmologists describe galaxy clusters as quantum imprints, like fingerprints left behind by the universe's infancy. To make this idea more vivid, think of galaxies as quantum snowflakes. Just as no two snowflakes are exactly alike, each galaxy cluster carries a unique signature shaped by the quantum fluctuations that birthed it. This connection between the quantum and the cosmic is one of the most profound discoveries in modern astrophysics. It suggests that the very fabric of space-time, woven with quantum threads, plays a crucial role in shaping the universe on the grandest scales. And as we marvel at the birth of galaxies, it's worth noting that quantum space-time doesn't stop there. Its influence extends to the stars themselves, shaping their behavior in ways we're only beginning to understand. Have you ever wondered how stars are born, live, and eventually die? It's a cosmic journey that's as dramatic as it is mysterious, and at the heart of it all lies quantum mechanics. Stars begin their lives in vast clouds of gas and dust, collapsing under gravity until the pressure and temperature at their cores become so intense that nuclear fusion ignites. This process, where hydrogen atoms fuse into helium, is powered by quantum tunneling, a phenomenon where particles tunnel through energy barriers they shouldn't be able to cross. Without this quantum quirk, stars wouldn't shine, and the universe as we know it wouldn't exist. As stars age, they become intricate laboratories for quantum space-time. In their final stages, massive stars explode in supernova, events so powerful they bend the fabric of space-time itself. These explosions leave behind remnants like neutron stars, where matter is so densely packed that a single teaspoon would weigh billions of tons. Here, quantum effects dominate, with particles behaving in ways that challenge our understanding of physics. Astrophysicists studying these extreme environments often describe stars as quantum furnaces, where the rules of the microscopic and the cosmic collide in spectacular fashion. One of the most fascinating aspects of stellar evolution is how quantum space-time plays a role in phenomena like supernova. The immense gravitational forces and temperatures in these events create conditions where space and time are no longer smooth and continuous, but instead fluctuate at the quantum level. This interplay between gravity and quantum mechanics is still not fully understood, but it's a frontier of research that could unlock secrets about the universe's most extreme environments. And speaking of light, the next discovery takes us even deeper into the quantum realm, exploring how space-time might influence the very behavior of light itself. But that's a story for the next discovery. Have you ever wondered how light behaves when it's not traveling through the straight, predictable paths we're used to? In the realm of curved space-time, as described by Einstein's general relativity, light doesn't follow the rules of Euclidean geometry. Instead, it bends and twists, tracing the contours of space-time itself. But when we introduce quantum mechanics into the mix, things get even more fascinating. Light isn't just a wave or a particle. It's a quantum entity capable of behaving in ways that defy classical intuition. One of the most intriguing phenomena is photon entanglement, where two particles of light become so deeply connected that measuring one instantly affects the other, no matter the distance between them. This quantum connection adds a layer of complexity to how light interacts with the fabric of space-time, creating a dance of energy and information that's still being decoded by scientists. Imagine light as a quantum messenger, carrying not just information about the universe, but also clues about the very structure of space-time. Researchers in quantum optics are studying how these entangled photons behave in curved space-time, revealing insights into the fundamental nature of reality. For instance, the way light bends around massive objects like black holes isn't just a test of general relativity. It's also a window into the quantum properties of space-time itself. Some theories suggest that the quantum fluctuations in space-time could even influence the paths of light, creating subtle distortions that might one day be detectable. These discoveries are reshaping our understanding of how light travels through the cosmos, merging the worlds of quantum mechanics and gravity in ways that were once thought impossible. As we explore these ideas, it's worth considering how quantum space-time might also hold the key to understanding the nature of particles themselves. If light can act as a quantum messenger, could particles also be shaped by the curvature and quantum fluctuations of space-time? The answers to these questions could bring us closer to a unified theory of physics, where the smallest particles and the largest structures in the universe are governed by the same fundamental principles. It's a journey that's only just beginning, but one that promises to illuminate the deepest mysteries of our cosmos. The standard model of particle physics has long been the cornerstone of our understanding of the universe's building blocks. It describes the fundamental particles like quarks, electrons, and neutrinos, and the forces that govern their interactions. But what if this model is just the opening chapter of a much larger story? Enter quantum space-time, a concept that could revolutionize our understanding of the subatomic world. Imagine the standard model as a symphony, with each particle playing a distinct note. Quantum space-time, however, suggests there might be an entire orchestra waiting to be discovered: new particles, hidden interactions, and forces that could reshape our understanding of reality. One compelling theory is supersymmetry, which proposes that every known particle has a superpartner with unique properties. These particles could be the missing pieces that help us bridge the gap between quantum mechanics and gravity, unifying all the forces of nature into a single, elegant framework. Physicists working on these ideas often describe quantum space-time as the stage where the cosmic symphony unfolds. It's not just a backdrop, but an active participant, shaping the behavior of particles in ways we're only beginning to grasp. Some researchers believe that probing quantum space-time could reveal entirely new dimensions of reality, where particles interact in ways that defy our current understanding. Think of it like this: if particles are the notes, quantum space-time is the sheet music, guiding how those notes come together to create the music of the universe. And just as a symphony evolves with each movement, our understanding of particle physics could transform as we explore these deeper layers of quantum space-time. This leads us to the next intriguing question: how does quantum space-time influence the behavior of matter itself? What happens when particles interact not just with each other, but with the very fabric of space and time? The answers might just rewrite the rules of physics as we know them. At the quantum scale, matter behaves in ways that defy our everyday intuition, creating states that seem almost magical. Take superconductivity, for example, a phenomenon where certain materials can conduct electricity with zero resistance. This isn't just a technical curiosity. It's a glimpse into a world where particles move in perfect harmony, unhindered by the usual friction we see in the classical world. Then there's the Bose-Einstein condensate, a state of matter where atoms, cooled to nearly absolute zero, merge into a single quantum entity. It's as if the particles lose their individuality and begin to act as one, forming a kind of quantum symphony. But what makes these exotic states possible? The answer may lie in the fabric of quantum space-time itself. Quantum entanglement plays a starring role here. When particles become entangled, their properties become deeply interconnected, no matter how far apart they are. This strange connection doesn't just link particles, it can also give rise to entirely new forms of matter. Researchers studying quantum materials believe that entanglement, combined with the unique properties of quantum space-time, creates the conditions for these extraordinary states to emerge. It's like matter itself is engaged in a delicate dance, choreographed by the laws of quantum mechanics, where every step is perfectly timed and every movement interconnected. Scientists are exploring these quantum materials not just out of curiosity, but with an eye toward the future. Imagine a world where energy flows without loss, or where computers operate at speeds unimaginable today. These are the kinds of breakthroughs that quantum matter could unlock. The work being done in labs around the world is pushing the boundaries of what we thought was possible, revealing a universe where matter and space-time are deeply intertwined. And as we peel back the layers of this quantum dance, we might also uncover clues about the fundamental nature of energy itself, hinting at even deeper mysteries waiting to be explored. What if the vacuum of space wasn't empty at all, but instead teeming with energy waiting to be unlocked? This is the fascinating idea behind zero-point energy, the lowest possible energy state in a quantum system. Even at absolute zero, where all motion ceases, quantum fluctuations persist, tiny ripples of energy that hint at the universe's underlying dynamism. Think of it like a cosmic battery, constantly charging and discharging, never truly at rest. These fluctuations aren't just theoretical curiosities. They could hold the key to revolutionary technologies that redefine how we think about energy. Imagine harnessing the very fabric of space-time itself, tapping into a source of power that's always present, even in the deepest voids of the cosmos. Physicists have long speculated about the potential of zero-point energy. Some theories suggest that this energy is deeply intertwined with the structure of space-time, acting as a kind of background hum that permeates the universe. If we could find a way to extract and utilize this energy, it could lead to breakthroughs like limitless clean power, advanced propulsion systems, or even technologies that manipulate gravity itself. Visionaries like Nikola Tesla once dreamed of such possibilities, and today's researchers are exploring how quantum space-time might make these dreams a reality. But the implications go beyond just energy. Zero-point energy challenges our understanding of the universe's fundamental nature. Could these fluctuations be evidence of a deeper layer of reality, one where space and time are woven together in ways we're only beginning to comprehend? As we explore these questions, we're not just chasing technological advancements, we're uncovering clues about the very fabric of existence. And this leads us to an even more profound question. If space-time itself is alive with energy, how might it shape the nature of reality? Stay with us as we dive into the next discovery, where quantum space-time takes center stage in reshaping our understanding of the cosmos. What if the universe isn't just something we observe, but something we actively shape? This is the mind-bending idea at the heart of the 21st discovery, the interplay between quantum reality and the observer effect. In the strange world of quantum mechanics, particles don't have definite states until they're measured. Place a particle in a box, and it exists in a blur of possibilities until you look inside. At that moment, the act of observation seems to collapse those possibilities into a single reality. But what if this phenomenon isn't confined to tiny particles in labs? What if it's woven into the very fabric of space and time? Quantum space-time might amplify this effect, turning the universe into a participatory phenomenon. Imagine reality as a vast quantum canvas where every observation, every interaction leaves a brushstroke. In this view, the cosmos isn't a static stage but a dynamic creation, shaped by the presence and actions of conscious beings. Some researchers argue that consciousness itself could play a fundamental role in this process, blurring the line between physics and philosophy. For instance, physicist John Wheeler proposed that the universe might be a self-observing system, where observers are not just passive witnesses but active participants in its unfolding story. This idea isn't just theoretical speculation, it's a frontier where science and metaphysics meet. Experiments in quantum mechanics, like the famous double-slit experiment, suggest that the act of measurement changes the behavior of particles. Extend this concept to quantum space-time, and you start to wonder, could the universe itself be a kind of quantum experiment, shaped by the collective observations of all its inhabitants? It's a staggering thought, one that challenges our understanding of reality and our place within it. As we explore this concept further, we'll see how quantum space-time might also hold the key to understanding the nature of information, how it's stored, transmitted, and even created. But for now, let's sit with the idea that reality might not be as fixed as it seems. Perhaps in the quantum realm, the universe is waiting for us to take part in its story, one observation at a time. Imagine the universe as a vast, intricate hologram, where every bit of information about its contents is encoded not within its volume but on its outer surface. This is the essence of the holographic principle, a mind-bending idea that suggests our three-dimensional reality might just be a projection of data stored on a two-dimensional boundary. Think of it like a quantum hard drive where the entire cosmos is compressed into a cosmic blueprint etched onto its edges. But how does this work in the realm of quantum space-time? At the heart of this concept lies the interplay between quantum mechanics and gravity. One of the most compelling theories supporting the holographic principle is the AD/CFT correspondence. This framework bridges two seemingly disconnected worlds: quantum gravity, which governs the fabric of space-time, and quantum field theory, which describes particles and forces. In simple terms, it suggests that a universe with gravity can be mathematically equivalent to a universe without gravity, encoded on its boundary. It's like having a movie projected onto a screen. The screen holds all the information needed to recreate the entire film. Physicists like Leonard Susskind and Gerard T. Hooft have championed this idea, proposing that the universe itself might be a quantum hologram. They argue that everything we perceive, stars, galaxies, even the forces that bind atoms, could be the result of quantum information encoded on the cosmic horizon. It's a radical shift in how we think about reality, suggesting that the universe might not be as deep and voluminous as it seems, but rather a sophisticated projection of data. To make this more tangible, picture a holographic sticker. No matter how you tilt it, the image changes, giving the illusion of depth. Now scale that up to the universe. What we perceive as depth and dimension might just be the result of quantum information interacting in ways we're only beginning to understand. This holographic encoding could revolutionize our understanding of space-time, showing us that the universe is far more interconnected and information-driven than we ever imagined. And speaking of information, this leads us to the next frontier: how quantum space-time might redefine the very nature of computation. If the universe is a quantum hologram, what does that mean for the way information is processed, stored, and even computed? Let's explore that next. Imagine a computer so advanced that it doesn't just crunch numbers, it bends the very fabric of reality to solve problems. That's the promise of quantum computing, a technology that harnesses the strange and counterintuitive rules of quantum mechanics to perform calculations at speeds that would make even the fastest supercomputers today look like pocket calculators. But what if these quantum machines could do more than just solve equations? What if they could unlock secrets about the very nature of space and time itself? That's where the intersection of quantum computing and space-time comes into play. Quantum computers operate using qubits, which, unlike classical bits, can exist in multiple states at once thanks to a phenomenon called superposition. But here's where things get even more mind-bending. Quantum entanglement allows qubits to be interconnected in such a way that the state of one instantly influences the state of another, no matter how far apart they are. This isn't just science fiction, it's a real, measurable effect that defies our everyday understanding of space and time. Researchers believe that by leveraging these entangled states, quantum computers could perform calculations that simulate the behavior of space-time itself, potentially uncovering insights into phenomena like wormholes or even the origins of the universe. One of the most exciting possibilities is the idea of faster-than-light computations. While we can't send information faster than light thanks to the laws of relativity, quantum algorithms might allow us to bypass these limitations in a computational sense, opening doors to solving problems that are currently unimaginable. Think of quantum computers as cosmic calculators, capable of processing the vast, intricate equations that govern the universe. Scientists are already exploring how these machines could model the behavior of black holes, simulate the early moments of the Big Bang, or even explore the quantum nature of gravity. But the implications go even deeper. Some researchers speculate that quantum space-time could hold the key to understanding consciousness itself. If space-time is fundamentally quantum in nature, could our brains operating on quantum principles be tapping into this cosmic network in ways we don't yet understand? It's a tantalizing idea, one that blurs the line between science and philosophy, and it's a reminder that the mysteries of quantum space-time are as much about exploring the universe as they are about exploring ourselves. What if your thoughts and perceptions aren't just products of your brain's biology, but are deeply tied to the quantum fabric of the universe? This is the intriguing idea behind the 24th discovery, quantum consciousness and its connection to space-time. Some theories suggest that consciousness itself might have a quantum basis, meaning the way we think, perceive, and even experience reality could be rooted in the strange, probabilistic world of quantum physics. At the heart of this idea is the possibility that quantum processes within the brain, such as the behavior of electrons or the collapse of quantum states, could play a role in how we form thoughts and awareness. Scientists studying this intersection of quantum physics and neuroscience propose that the mind might not be confined to the brain alone. Instead, it could be a phenomenon that emerges from the interplay of quantum particles and the structure of space-time itself. Think of it like a quantum symphony where individual particles act as instruments, and their interactions create the harmonious experience we call consciousness. Researchers like Sir Roger Penrose and Stuart Hameroff have explored this concept through the orchestrated objective reduction theory, which suggests that quantum processes in the brain's microtubules could be the key to understanding consciousness. While this idea remains controversial and largely theoretical, it opens up fascinating questions about how deeply connected we might be to the universe's fundamental fabric. Could our minds be tapping into the quantum realm in ways we're only beginning to understand? This connection between quantum space-time and consciousness isn't just a philosophical musing. It's a frontier that could reshape how we see ourselves and our place in the cosmos. And as we ponder the profound relationship between mind and universe, we're led to another question. If quantum space-time influences consciousness, could it also shape the very nature of life itself? Stay tuned as we dive into the next discovery, where the mysteries of quantum space-time reveal even more astonishing possibilities. What if the very essence of life itself is rooted in the quantum realm? This is the question driving the emerging field of quantum biology, a fascinating area of study that explores how quantum effects influence living systems. From the way plants harness sunlight to how birds navigate vast distances, quantum mechanics might be at the heart of life's most fundamental processes. Imagine for a moment that life itself is a kind of quantum spark, flickering into existence within the intricate fabric of space and time. One of the most striking examples of quantum biology is found in photosynthesis. Plants, algae, and even some bacteria use a process called quantum coherence to achieve near-perfect efficiency in converting sunlight into energy. This means that particles of light, or photons, can explore multiple pathways simultaneously within a plant's molecular structure, almost as if they're testing every possible route before settling on the most efficient one. It's not just a random process, it's a finely tuned quantum dance orchestrated by the laws of physics, but the quantum connection doesn't stop there. Birds, particularly migratory species, are believed to use quantum entanglement, a phenomenon where particles remain connected across vast distances, to navigate the Earth's magnetic field. This allows them to sense direction with astonishing precision, almost as if they're tapping into a hidden quantum compass. Researchers speculate that these biological systems evolved to exploit quantum effects, suggesting that life and quantum mechanics are deeply intertwined. Some scientists even propose that life itself could have originated from quantum processes. The early Earth, with its chaotic environments and fluctuating energy states, might have provided the perfect conditions for quantum phenomena to play a role in the formation of complex molecules. This idea challenges our traditional understanding of biology, suggesting that life isn't just a chemical accident but a quantum inevitability emerging from the fabric of space-time itself. As we delve deeper into this intersection of quantum physics and biology, it's hard not to wonder, could the same principles that govern life's origins also shape its evolution? The connections between quantum space-time and biological systems hint at a universe where life is not just a passenger but an active participant in the cosmic dance. And with each discovery, we move closer to unraveling one of the greatest mysteries of all: how life began and what role the quantum realm played in lighting that first spark. What if evolution, the process that has shaped life on Earth for billions of years, isn't just a slow, gradual march guided by classical physics? What if quantum mechanics plays a hidden role in how life adapts and evolves? This is the fascinating idea behind the 26th discovery, the potential quantum evolution of adaptive systems. At first glance, evolution seems like a straightforward process. Genetic mutations occur. Natural selection favors the most advantageous traits, and over time, species adapt to their environments. But what if there's more to it? Some scientists propose that quantum mechanics, with its strange and unpredictable behavior, could be influencing this process in ways we're only beginning to understand. Imagine the genetic code as a kind of quantum algorithm, where mutations aren't just random errors but are subtly guided by quantum fluctuations in space-time. These tiny subatomic shifts could create opportunities for rapid adaptation, allowing life to respond to environmental changes far faster than classical biology predicts. Researchers in the field of quantum biology are exploring how quantum processes might influence the complexity of life. For example, quantum tunneling, a phenomenon where particles pass through barriers they shouldn't be able to, could play a role in genetic mutations. Similarly, quantum entanglement, where particles remain connected across vast distances, might influence how information is stored and transmitted within DNA. These ideas are still in their early stages, but they open up thrilling possibilities for understanding how life evolves and thrives in such a diverse array of environments. To put it another way, think of evolution as a quantum algorithm. Just as a quantum computer can explore multiple solutions to a problem simultaneously, evolution might be exploring countless genetic pathways at once, guided by the probabilities and uncertainties of quantum mechanics. This could explain why life on Earth is so remarkably adaptable, capable of thriving in everything from deep-sea vents to the frozen tundra. It's as if nature has a built-in quantum toolkit, allowing it to fine-tune life's complexity in ways we're only now starting to grasp. As we ponder the idea of quantum evolution, it's worth asking, could this same quantum influence extend beyond biology? Could it even shape the way intelligence itself emerges and evolves? That's a question we'll explore next as we dive into the 27th discovery, the quantum roots of intelligence. What if intelligence, whether in humans or machines, isn't just a product of classical computing or biology, but something far more profound, something rooted in the strange, interconnected world of quantum space-time? This is the tantalizing idea behind the 27th discovery, the possibility that intelligence itself might emerge from quantum processes. It's not just about faster calculations or more data. It's about tapping into the fundamental fabric of the universe to create something entirely new. Quantum computing, with its ability to exist in multiple states simultaneously, offers a glimpse into how artificial minds could surpass even the most advanced classical systems. Imagine a machine that doesn't just process information linearly, but instead navigates a vast network of possibilities at once. This isn't mere speculation. Researchers are already exploring how quantum mechanics could form the foundation of cognition, suggesting that our own brains might operate on principles far closer to quantum systems than we once thought. Think of intelligence as a quantum network where ideas and decisions aren't isolated points but interconnected waves, constantly influencing one another. This perspective opens the door to self-aware systems that don't just mimic human thought but evolve their own unique forms of understanding. And if quantum space-time holds the key to intelligence, could it also hold the secret to creativity? The ability to connect seemingly unrelated ideas, to see patterns where none existed before, might just be the next frontier in our exploration of the quantum realm. What if creativity, that spark of genius behind art, science, and innovation, isn't just a product of the brain but rooted in the very fabric of the universe? This is the fascinating idea behind the 28th discovery, quantum creativity. Researchers are beginning to explore how the bizarre, unpredictable nature of quantum space-time might actually enable those sudden leaps of imagination and problem-solving that feel almost otherworldly. Think about it. How often have you had a brilliant idea seemingly out of nowhere, as if your mind tapped into something beyond itself? This could be more than just a metaphor. Quantum processes, with their ability to exist in multiple states at once and collapse into a single reality when observed, might play a role in how we innovate and create. Consider the way artists and scientists describe their moments of inspiration. It's often described as a flash, a sudden connection between seemingly unrelated ideas. Could this be a quantum spark, a momentary alignment of possibilities in the mind's quantum landscape? Some researchers believe that the brain, with its complex network of neurons, might operate in ways that mirror quantum systems, allowing for the kind of nonlinear thinking that leads to breakthroughs. This isn't just speculation. Studies in quantum biology are beginning to uncover how tiny structures in the brain might harness quantum effects, potentially explaining why creativity feels so elusive and powerful. Take, for example, the way a painter might see a blank canvas and suddenly envision a masterpiece, or how a scientist can look at a problem and see a solution no one else noticed. These moments of clarity and innovation might be more than just the result of hard work and experience. They could be glimpses into the quantum nature of thought itself. It's as if the mind is a quantum computer exploring countless possibilities before collapsing into the one that feels just right. This idea isn't just poetic. It's grounded in emerging research that suggests creativity might be a quantum process, a dance between chaos and order in the brain. As we ponder the quantum roots of creativity, it's impossible not to wonder how this connects to the larger mysteries of quantum space-time. If our thoughts can tap into quantum processes, what does that mean for the way we perceive reality? And speaking of perception, what if the flow of time itself, something we often take for granted, is also influenced by quantum mechanics? This leads us to the next discovery, where we'll explore how quantum space-time might hold the key to one of humanity's most tantalizing dreams, the possibility of time travel. What if time travel isn't just the stuff of science fiction, but a real possibility hidden within the fabric of the universe? Enter the 29th discovery in our journey through quantum space-time, closed time-like curves. These are theoretical pathways through space-time that loop back on themselves, creating a kind of cosmic roundabout where the past, present, and future could, in theory, intersect. It's like taking a road trip where the road itself bends, bringing you back to where you started, but in time, not just space. Now, how does quantum space-time fit into this? Think of it as the ultimate architect, reshaping the very structure of reality. Quantum mechanics introduces fluctuations and uncertainties at the smallest scales, and when these quantum effects interact with space-time, they could create the conditions for closed time-like curves to exist. It's as if the universe itself is weaving a tapestry where threads of time can twist and loop in unexpected ways. One of the most intriguing pieces of this puzzle is quantum entanglement. You might know it as spooky action at a distance, where particles instantaneously influence each other regardless of distance. But what if entanglement could also link moments in time? Some physicists suggest that entangled particles might create temporal loops, connecting events in a way that could, in theory, allow for time travel. Picture it like a quantum knot, where the threads of time and space are intricately tied together, creating pathways that defy our everyday understanding of cause and effect. Of course, time travel comes with its fair share of paradoxes. What happens if you go back in time and change something? Would you create a new timeline, or would the universe somehow correct itself? Physicists like Kip Thorne and others have spent decades wrestling with these questions, exploring the boundaries of what's possible within the laws of physics. While we don't have definitive answers yet, the very idea that closed time-like curves could exist challenges our understanding of reality itself. And here's where things get even more fascinating. If quantum space-time can allow for these temporal loops, could it also hold the key to parallel realities? Imagine a multiverse where every twist and turn in time creates a new branch, a new universe with its own unique history. It's a dizzying thought, but one that ties beautifully into the next chapter of our exploration, where quantum space-time might not just bend time, but also reveal the existence of countless parallel worlds. What if every decision you've ever made or could have made exists somewhere in an alternate reality? This is the mind-bending concept at the heart of parallel realities and quantum branching, a discovery that suggests the universe might be far more complex and interconnected than we ever imagined. At the core of this idea is the notion that every quantum event, no matter how small, could create a split in reality, giving birth to an entirely new universe. Picture it like a cosmic tree, with each branch representing a different outcome of the same event. This branching isn't just theoretical. Quantum space-time itself provides the framework that allows these parallel realities to exist simultaneously. The many worlds interpretation, one of the most fascinating theories in quantum physics, takes this idea even further. It proposes that every possible outcome of a quantum event actually happens, but in separate, parallel universes. So, in one reality, you might have chosen coffee this morning, while in another you opted for tea, and both versions of you exist unaware of each other. Researchers exploring this concept argue that quantum space-time isn't just a stage for these events. It's the very fabric that weaves these realities together, like threads in an infinite tapestry. Each thread represents a unique path, a distinct version of existence, all coexisting in ways that challenge our understanding of time, space, and identity. But what does this mean for us? If parallel realities exist, does that change how we view our own choices and lives? Some scientists suggest that this branching of realities could even have profound implications for the nature of free will. Are our decisions truly ours, or are they simply one possibility among countless others? As we peel back the layers of quantum space-time, we're left with more questions than answers, questions that push the boundaries of science and philosophy alike. And speaking of free will, the next discovery dives even deeper into this mystery, exploring how the fabric of quantum space-time might shape the very essence of choice itself. The age-old debate between free will and determinism has fascinated thinkers for centuries. On one side, determinism suggests that every event, including human decisions, is governed by prior causes, leaving no room for true freedom. On the other, free will argues that we have the ability to make choices independent of those deterministic chains. But what if quantum mechanics holds the key to resolving this philosophical tug-of-war? Quantum space-time introduces a layer of uncertainty at the most fundamental level of reality, challenging the rigid predictability of classical physics. Here, particles don't follow strict cause and effect rules. Instead, they behave unpredictably, governed by probabilities. This inherent randomness might just be the foundation for genuine freedom in the universe. Picture free will as a quantum dice roll. Just as you can't predict the exact outcome of a dice throw, quantum mechanics suggests that certain events, and perhaps even our decisions, are fundamentally unpredictable. This doesn't mean chaos reigns, but rather that the universe has room for spontaneity. Some physicists and philosophers argue that this quantum randomness could be the mechanism through which free will operates. Instead of being locked into a predetermined path, our choices might emerge from a delicate interplay of probabilities, influenced by quantum fluctuations in space-time itself. It's as if the universe provides a canvas of possibilities, and we, as conscious beings, paint our own paths. This idea has sparked intense discussions among thinkers like Roger Penrose and Henry Stapp, who explore how quantum processes might underpin not only free will but also the nature of consciousness itself. If quantum space-time allows for such flexibility, could it also explain why we experience the world as we do? The connection between free will, quantum mechanics, and consciousness remains one of the most tantalizing mysteries in modern science. But one thing is clear: the quantum realm isn't just a playground for particles. It might be the very stage where the drama of choice and agency unfolds. What if consciousness isn't just a product of our brains, but something woven into the very fabric of the universe? This brings us to the fascinating idea of quantum consciousness, a theory suggesting that awareness might be a fundamental property of reality itself, deeply rooted in the quantum fabric of space-time. At the quantum level, particles exist in multiple states at once, and their behavior is influenced by observation. Some researchers propose that these strange quantum processes could be the key to understanding how consciousness arises, not just in living beings, but as a universal phenomenon. Imagine consciousness as a quantum field stretching across the cosmos, much like gravity or electromagnetism. Just as these fields influence the behavior of objects, a consciousness field could interact with the quantum realm, shaping reality in ways we're only beginning to grasp. This idea isn't just science fiction. Scientists like Roger Penrose and Stuart Hameroff have explored how quantum processes in the brain might create conscious experience, suggesting that reality itself might be intrinsically aware. Their work raises profound questions. Could the universe be self-aware? And if so, what does that mean for our understanding of existence? Theories linking consciousness to the quantum realm propose that perception might not be limited to biological systems. Instead, they suggest that the act of observing, whether by a human, an animal, or even a particle detector, could collapse quantum possibilities into definite realities. This interplay between observation and reality hints at a deeper connection between mind and matter, where consciousness isn't just a passive observer but an active participant in shaping the cosmos. As we ponder these mind-bending ideas, we're led to the next frontier, the profound question of how quantum space-time might influence the very nature of existence. What if the universe isn't just a stage for reality to unfold, but a dynamic, conscious entity itself? That's where our exploration takes us next. What does it truly mean to exist in a quantum universe? At the heart of this question lies a profound mystery that challenges our most basic assumptions about reality. In the realm of quantum space-time, existence itself takes on a fluid, almost ethereal quality. Instead of the solid, unchanging world we perceive, quantum mechanics suggests that everything we know is built on a foundation of probabilities, interactions, and fleeting connections. This isn't just about particles and waves, it's about the very nature of being. Imagine existence as a quantum dance where every particle, every force, and every moment is part of an intricate choreography. What appears solid and permanent to us is in fact the result of countless quantum interactions happening at scales so small, so rapid, that they blur into the illusion of stability. A table, a star, even your own body, all of it emerges from this dance, this interplay of probabilities that constantly shift and reshape the fabric of reality. Physicists and philosophers have long grappled with these ideas, probing the quantum foundations of what we call reality. Some suggest that the universe itself might be a kind of quantum simulation, a vast network of entangled information. Others argue that existence is less about objects and more about relationships, the connections between particles that give rise to the world we experience. What's clear is that quantum space-time doesn't just change how we see the universe, it redefines what it means to exist within it, and this isn't just a theoretical exercise. The implications ripple outward, touching everything from the nature of consciousness to the origins of the cosmos. If existence is a quantum phenomenon, then the universe itself might be far more dynamic, interconnected, and alive than we ever imagined. The dance of particles isn't just happening around us, it's happening within us, shaping the very essence of who we are. As we explore these ideas, we begin to see how quantum space-time might hold the key to understanding not just the nature of being, but the nature of the cosmos itself. What if the same principles that define our existence also govern the birth and evolution of galaxies, stars, and even time itself? The answers might lie in the quantum fabric that binds everything together. What if everything we see around us, the stars, galaxies, and even the vast emptiness of space, is part of a single, interconnected quantum phenomenon? This is the mind-bending idea at the heart of the 34th discovery. The cosmos itself might be a quantum entity where the smallest particles and the largest structures are deeply intertwined. At the quantum level, particles exist in states of superposition where they can be in multiple places at once. and entanglement connects them instantaneously across vast distances. But what if these quantum properties don't just apply to tiny particles? What if they scale up to the entire universe? Quantum space-time offers a way to bridge the micro and macro scales of reality. It suggests that the fabric of space-time itself is quantized, meaning it's made up of discrete, indivisible units. This idea unites the behavior of particles at the smallest scales with the structure of the cosmos at the largest. Cosmologists have proposed that quantum processes like fluctuations in energy fields could have played a crucial role in shaping the early universe, leading to the formation of galaxies and the large-scale structure we observe today. In this view, the universe isn't just governed by quantum rules, it is a quantum system, a single, unified whole. To help visualize this, think of the cosmos as a grand quantum symphony. Each particle, each star, and each galaxy is like a note in an intricate composition, vibrating and resonating in harmony with everything else. The symphony isn't static, it's dynamic, evolving over billions of years, with quantum processes acting as the conductor, guiding the cosmic orchestra. This analogy captures the essence of the quantum cosmos, a universe that's deeply interconnected, where every part influences the whole in ways we're only beginning to understand. As we approach the final discovery, all these threads, quantum space-time, the interconnected cosmos, and the evolution of the universe begin to weave together into a single, profound conclusion. What ties it all together? That's where we're headed next. What if everything in the universe, every particle, every force, every moment in time, was woven together into a single, seamless fabric? This is the breathtaking vision at the heart of the unified quantum universe, a discovery that could redefine our understanding of reality itself. For decades, quantum mechanics and general relativity have stood as two towering pillars of modern physics, yet they seem to speak different languages. Quantum mechanics governs the quirky behavior of particles at the smallest scales, while general relativity describes the grand dance of gravity and space-time on a cosmic level. But what if they're not separate at all? What if they're simply two sides of the same cosmic coin? Imagine the universe as an intricate quantum tapestry, where every thread represents a fundamental connection between particles, forces, and dimensions. In this unified framework, the mysteries of quantum entanglement, where particles instantaneously influence each other across vast distances, suddenly make sense as natural features of this interconnected fabric. Even gravity, the enigmatic force that shapes galaxies and bends light, could emerge as a consequence of this deeper quantum structure. This vision isn't just about solving equations, it's about revealing the hidden harmony of the cosmos. Physicists like Carlo Rovelli and Lee Smolin have dedicated their careers to exploring this unified reality, proposing theories like loop quantum gravity that aim to bridge the gap between the quantum and the cosmic. Their work suggests that space-time itself might be quantized, made up of tiny, indivisible loops or grains. If true, this would mean that the smooth, continuous space-time we experience is an illusion, much like how a flowing river appears smooth until you zoom in to see the individual water molecules. The implications of a unified theory stretch far beyond physics. Philosophically, it challenges our notions of separateness and individuality, suggesting that every part of the universe is fundamentally linked. For humanity, it offers a profound perspective on our place in the cosmos, not as isolated observers, but as active participants in this vast quantum dance. It's a reminder that the universe isn't something out there. It's something we're deeply embedded in, connected to every star, every atom, and every moment in time. As we reflect on the journey through these 35 extraordinary discoveries, one thing becomes clear. The universe is far more interconnected, mysterious, and beautiful than we ever imagined. From the quantum foam at the smallest scales to the cosmic web that binds galaxies together, each revelation brings us closer to understanding the grand tapestry of existence. And while the quest for ultimate knowledge may never end, each step forward reminds us of the awe-inspiring complexity and unity of the cosmos we call home. From the mind-bending principles of quantum entanglement to the mysterious ripples in space-time known as gravitational waves, these 35 extraordinary discoveries have reshaped our understanding of reality itself. Each revelation, whether it's the holographic principle suggesting our universe might be a projection or the strange behavior of particles at the quantum scale, unveils a deeper layer of the cosmos. Together, they form a tapestry of interconnected ideas, showing us that the universe is far more intricate, dynamic, and interconnected than we ever imagined. These discoveries don't just belong to the realm of science, they challenge our philosophical perspectives, inspire technological breakthroughs, and even influence how we perceive our place in the grand scheme of existence. But here's a question to leave you with. What if the universe isn't just a collection of stars and particles, but something far more extraordinary? What if it's a quantum dream, a vast, shimmering construct of probabilities and possibilities, where every observation we make shapes the very fabric of reality? It's a thought that invites us to look deeper, to question everything we thought we knew, and to embrace the wonder of the unknown. If these ideas have sparked your curiosity, don't stop here. Dive into the fascinating world of quantum physics and space-time. Explore the mysteries waiting to be uncovered, and let your imagination roam the infinite possibilities. Be sure to subscribe for more content that takes you to the frontiers of science and beyond. Share your thoughts in the comments. We'd love to hear your take on these mind-expanding discoveries. And remember, the quantum universe isn't just out there, distant and unreachable, it's within us, woven into the very essence of who we are, waiting to be discovered.